let me briefly introduce us, about Swat sir. So he is currently working as an assistant professor at IIT Dharwad. He has obtained his PhD degree from IIT Kanpur in physics. His research interest includes quantum itself. So that is the beauty of the sessions that we are going to have today and tomorrow. His area of research interest includes quantum information theory, optics and nonlinear optics, the quantum again, and nonlinear dynamics of optical systems. So with this, I would like to hand over the session to Aswat sir. And sir, you may start the session.
Thank you very much, sir. I hope participants can hear me loud and clear.
Yes, sir.
Great. Okay. So very good afternoon to all the participants. So like sir was saying, we would be talking about the differential equations, discussing more about differential equations. Okay. So even though if you just see the flow of the content for this particular FTP, let me show you. Here you see, even though my part is today the numerical integration and differential equations, particularly second order ordinary differential equations with the constant coefficients, that is on the first day, and the second day is linear second order ordinary differential equations, in short ODEs, with variable coefficients and boundary value problems. Okay, right? So these are the two day sessions which I have to be going to be covering. Okay, so yeah, I can just straight away go into numerical integration. That would it would not give the flavor properly. Okay, so what I thought, let's say, will come from the very simple, from the crux, very start, so that we will build up to that point. And so the connection to the current FTP topics is numerical integration. Okay, right? Even though the actual integration would not, like, you are not going to do it on paper, right? So you are going to implement the integration in the programming on the system, like sir was saying earlier. You, for example, while studying the qubits and all, okay, so there we would be needing some numerical integration method. Okay, so that we will definitely discuss as a part of these 2 day sessions. Okay, so if I have asked for one more extra day, if I get some extra day somewhere during this the entire few days, what I would be doing, I would be showing the actual numerical integration using Python. Okay, whatever things which we will discuss today and tomorrow, we will see in detail the coding also, and that would, you can use it for the hands-on session somewhere, and also you could use the same for later the actual integration which you need to do, for example, in the quantum computing case. Okay, right? Fine. So like earlier FTPs, I would be using most of my hand notes to explain, and later on I will share my hand notes, also my lecture notes separately to the canvas. I will add, you people can go through and understand. Okay, so let me start. Right, you can see now the differential equations. Yeah, fine. So let's define what is differential equation in the first place. As we all know what is differential equations, so we see things and perceive things in certain way. Okay, that exact form we will, like, usually we take it for granted. Okay, so let's understand that, and let's revise that systematically. Okay, if I have to define what is differential equation, what it would be is, it is an equation for sure Okay, right? And it relates, interestingly, you see, it relates a given function f to one or more of its derivative. Okay, that is what the differential equation is mathematically. So what I mean is, if I have a function f, let's say it is depending on some independent variable x. Okay, so what differential equation does is it relates f of x to f star f prime, which is actually derivative of f with respect to x, and f double star, which is second order derivative of f with respect to same independent variable. Okay, so that is what a differential equation does. It relates given function to its derivative. Why it is required, we will see. Okay, so basically the relation means it's coming together. Let me write down a differential equation. Okay, we will just see whether it is a differential equation or not. Okay, okay, so let me erase that, write neatly. 2 into df by dx plus f of x, all the way f of x is a function of x, is equal to, let's say, 0. Or if you want, I don't want to confine to particular case, you can even say something else is there on the right hand side. It's another function of x. Okay, yes, whether does it satisfy to be a differential equation? Yes, because it has a derivative of second order, means power 2, and derivative of first order it has, and it has a function and its derivatives are all there, and it has an independent variable x is there. Yes, it is a differential equation. Okay, right? And so what we have to do with that is we have to solve it. Okay, so by solving it, we would know, solving would imply, would know how the function would behave with respect to, behaves with respect to x, that we would get to know, right? So whenever a differential equation is, we will just intended unknowingly try to solve. Why we unknowingly solve is, let's say take the nature. Okay, let's take the nature, right? In the nature, there are so many things are involved. Okay, let's say we try to explain things around us using physics. Okay, some mechanics are involved, we will use engineering. Okay, something mixing up, some chemicals mixing up, giving some other chemical, is a chemistry. Okay, let's say you take how plants make their energy out from the minerals from the ground and taking a sunlight, it is actually a biological process, photosynthesis. There is a biology or biotechnology, you can say. Okay, so you take any of these real world scenarios involving the different activities which are explained by the laws of physics. Okay, so there is a laws, those laws would be used to explain, laws would explain the activities. Okay, right? So these laws are actually written in terms of, written in terms of differential equations. Okay, so the differential equations one need to solve to get more insights. Okay, that is what I'm saying. Okay, right? So now, for example, let's take solving. When I say solving something, means what comes to our mind straight away is algebraic equations. Let's say I have an algebraic equation let's say I have x plus is equal to 3, x plus y is equal to 3. Let's say 2x plus 3y is equal to 8. I have two algebraic equations, two unknowns. How do you solve? Use some linear algebraic techniques and you will solve. Okay, you will solve and find what is x, what is y. Okay, so interestingly, when you try to solve, what happens? You would get specific x and y values. Okay, specific values you will get. Okay, but sometimes we may get a set of x comma y's as a solution. That is possible. Okay, right? Few set, not too many. But when I go for a differential equation, okay, however, in the case of D's, by solving, you would be getting a function, okay, so which is not a single solution. It is not a single solution. What I mean is, you would be getting a function. Function is what? A function is f of x with respect to x is some curve. Okay, some curve, right? So the differential equations solving would give multiple possible such functions. Okay, f of x, many possible. So it is called many curves. So family of curves, curve family, right? So there is a many curves are possible for a given same differential equations. When you try to solve, you would get many. That is the main important thing. That is what we usually take it for granted and we will just ignore it. Okay, so by solving differential equations, you get one or more functions, unlike algebraic scenario, right? So the obtained functions are actually the obtained solutions, or you can say functions, okay, represented by a family of curves. Okay, where each curve is a relation between dependent variable to independent variable. Okay, right? Very important, right? So what do we do? Just take a simple example. Okay, let's take a simple example and try to understand, right? Okay, so let me take a simple example. A simple example of D. I'm not saying whether it's a one dimension or two dimension. Sorry, it's a first order, second order, homogeneous, non-homogeneous. All those things will come later. So we are trying to define from the very scratch. Okay. So let me take a simple differential equation, which I am calling dy by dx is equal to. Let me take a simple equation. What I was saying earlier, I need to have a function and its derivative, which is connected or equated or together, they are put together. So this is a differential equation, the simplest differential equation, which says a derivative of a function, very important, you concentrate, derivative of a function is equal to itself. So that is the equation I have, differential equation I have. Okay, so how to solve this? Very simple. We have gone through it. So that is the way we do it is send like terms onto one side, send this to the left, x to the right, which is equal to dx. Okay, let's say I don't know what are the limits. So what I'll do, I'll integrate on the both the sides. Okay, so left hand side integration is 1 over y dy integration would give me log of y, natural log I'll write. On the right hand side I have integration of dx is just x. Since I have not substituted any limits, let me call some constant would creep in if I don't substitute any limits. If I substitute limits, the c prime is taken care. Okay, now I can send the left hand side log, natural log to right side. It becomes exponential. What I'll get, y of x is equal to exponential x plus c prime, which is equal to exponential c prime exponential x. Let me call exponential c prime as some c, which is equal to c into exponential x. So I got a solution. Okay, y of x is equal to c into exponential x, right? Okay, so this is the simplest way we usually find the solution of a differential equations. Okay, right? So by knowing the limits would imply what is c. Okay, if somebody given you limits, no need to bother about c, it is taken care. Now the motivation I was giving you here, in the case of physics, in the case of engineering, in the case of chemistry, biology, everywhere, even the astronomy, start from minute atomic level, let's say from atomic level to astronomical level, if you take every dynamics could be explained or described, or you can say you can described using differential equations. Okay, that is why we need to study them, that is why we need to know how to solve them. Okay, so let's take a simple example in the physics itself, in the physics. Okay, the first thing is the real world around us, the classical world, okay, where we can see and perceive things. So that world, if you just take and try to see, let's try to explain what that real scenario is. Let's say I have some mass m, okay, right? I hold it and just leave it. Okay, I'm just raising it. Let's say I raise my mobile and just leave it. It has, let's say, mass m, and when I leave it, because of the gravity, as we know, the gravity is there always, acceleration due to gravity, which is trying to pull the things towards the floor of the surface of the ground. Okay, so because of the gravity, there is a force generated on the system. What is that force? Is gravitational force, which is equal to the mass of the system multiplied by acceleration due to gravity, g value. So exactly z value is 9.8 meter per second square at the surface. In which direction? In towards it. Okay, so that is the direction, 9.8 meter per second square towards it. Okay, the direction you should remember. Right, now I got what is the gravitational force acting on the system. Okay, so because of that, the body is actually moving down, and not just moving with a constant velocity, it is actually accelerating. So initially the velocity is small, later on it picks up the velocity. As the point it is trying to touch the floor, the velocity becomes so maximum, right? So that much the acceleration is happening, increase in the velocity is taking, the velocity is changing. So there is a change in the velocity, it is going to give me the acceleration. So how to connect the acceleration to the exerted force is usually by Newton's law, right? Newton's law. Newton says that if there is any force acting on the system, Newton's second law, right? That is what saying. I want to explain this falling body, I would use Newton's second law. What it says, if there is a force acting on a body of mass m would create an acceleration some a with a vectorial symbol. So here in my scenario, the falling body case, what is a force? It's a force is gravitational force. Okay, so the mass is there as it is on the right, and acceleration. Now acceleration is what? Acceleration is rate of change of velocity. Okay, by the way, what is the velocity? Velocity is rate of change of position. Okay, let's say the position, let's say this is a floor, the object is here, so the position at any given time is, let's represented by a vector y, and that y vector is changing with respect to time, so that would be its velocity vector, and that velocity vector itself changing, so that would be acceleration. So the acceleration is second order derivative of position with respect to time. So let me substitute here m d square y by dt square. Usually people ignore putting the vectorial symbol. It's better to put a vectorial symbol. Okay. So now you see m gets cancels. I got a differential equation which is which is g equal to d square y by dt square. Okay, right? So now this is a differential equation. If I'm solving, let's say I want to solve, what I do, solve, I'll just take only magnitudes and try to solve. Okay, solving only considering magnitudes. Later on I can add this directions. Okay, right? Now so this is a very simple scenario. There is a second order derivative is involved. Let's say I want to even involve the first order derivative in the same setup. Okay, so how do I involve is, let's say the mass is falling. Okay, it's try to fall, right? Because of there is a air particles. Okay, the air particles would exert some resistive force or rigid force opposite in opposite direction, some resistive force exerted. So that, let's say that resistive force is Fr. In addition to Fg, in addition to gravitational force, gravity, Fg, if there is a resistive force from the air particle, then things become much more interesting. Let me call that force is Fr, like are saying. So the floor is here, particle is falling through the air. Okay, so as per basic simple physics rules or fundamental rules, what it was found is the resistive force is directly proportional to the velocity of the particle, right? So if the velocity is more resistive force is there. Velocity is less resistive force. So I can just simply write that as minus dy by dt. Okay. Now, if I want, the proportionality symbol is there. If I want to explicitly write down what is the resistive force, it will be some constant d dy by dt. Okay, so this is resistive force. Now I got the resistive force. Here k is a proportionality constant. Some proportionality constant. Okay, depending on, it depends on density of the air or even temperature and so on other factors. Okay, density, right, etc. So that k, somebody has captured k and given to us, it's fine with us. So okay, now let me write down the overall setup, overall equation. If I have to write down, what it would be is, of the two forces acting on the system is, one is gravity and there is a resistive force giving some acceleration to the system. Okay, so let me write down now explicitly what it is. I have mass into gravity of gravitational force and resistive force is equal to mass into, okay, dy by dt square. Okay, so now I got some equation. Let me multiply entire equation by 1 over m. So what I left with is d square y by dt square is equal to g minus k by m dy by dt. Okay, let's put everything together. It would be nice to see in that way. So d square y by dt square plus k by m dy by dt minus g is equal to 0. Okay, so now you see I have created a differential equation having second derivative and also the first derivative. Okay, so a falling object is described by falling object is described by a second order differential equation. So to understand exactly what happens, okay, what happens to object, one needs to solve DE and understand. Okay, somebody is saying, can you go up? Let me see what is the question. Can you go up? Okay, let me go up. Okay, just suppose type the question. What is the question? Manish Datta, sorry, Mrinal Datta. Okay, so what I did is I just initially I said there is an object which is falling. The force acting on it is gravitational force, m into gravity, which generates some acceleration in the system. So Newton's second law says F is equal to ma, where F is a gravitational force and m into a I'll just write down. So I got a differential equations of second order. Okay, now I want to explicitly discuss, I'm going to explicitly discuss exactly what happens in a falling object scenario. So there is a resistive force also that I captured and also added into the system. Okay, so the Newton's law now, on the left hand side I have a Newton's law, right? On the left hand side I have two forces, one is gravity force, another one is resistive force. Remember, the resistive force is opposite to the action of the velocity. Okay, that's why the minus sign. Okay, the minus sign, right? Okay, the minus sign indicates resistivity, resistive force, or the direction is opposite, right? Now to understand this setup, we have to solve this differential equation and try to understand. Okay, now this differential equation has second order and first order. Okay, it has everything in it. But remember, sometimes, let's say if I have specifically I have given y, so here y is a function of x only. Okay, let's say y is a function of, if y is function of x comma t, it's a two functions, two independent variables, right? Y is depending on two variables. In that case, we might involve the partial derivatives. What is the partial derivative is, I just vary the y with respect to only change in x. Okay, I may get one function. I may vary y, or I may vary independent variable t and see how much y is changing. That would be another derivative. So there are two kinds of derivatives emerge when a given function is dependent on two independent variables. Okay, very important, right? So the partial differential equations would arise in that scenario. Okay, and we need to solve them accordingly. We will see this scenario as we go through the sessions. Okay, remember when these things will come, right? I'm sorry. Right, so let's see some differential equations. Let's get to get a taste of some differential equations. Okay, so the taste of differential equations types. Okay, right. Okay, now something happened here. Reload. Yeah, so test of differential equations. Let's get some test of differential equations. Okay, so let me consider an example. What examples I'll be taking? Let me take a dy by dx is equal to x. Okay, so the derivative of a function is equal to its independent variable. Very simple. Okay, right? So in short, usually we'll write y prime is equal to x. Okay, remember the prime would refer to derivative with respect to x. Remember, so in some cases prime is only reserved for a time derivative, but right now we are at the initial stage. Let's reserve prime for any cases, either x or y. Since I have only x then independent variable here, so I have chosen that. So now let me, this differential equation is there. I don't know anything about this. I want to understand what it is describing. To know what it is describing, okay, one needs to solve it. Solve, right? So let's solve it. How do I solve? I just try to rearrange. The first thing comes to my mind is try to rearrange things in such a way I'll see like terms on one side. Okay, so the dy is on the left, x is on the right. I can integrate now simply. Okay, so integration on the left gives me what? Y. On the right I get x square by 2. Okay, since I am not taking exact limits, so I need to add some constant which takes care of the scenario of not putting some constant the limits. Okay, if I have a limits explicitly put, the c is not needed to add. So this is c is some arbitrary constant. Okay, right? You would find. Now if you just carefully see this particular equation, okay, y equal to x square by 2 plus c. If you just see this particular equation, okay, and try to just plot it. The best way is to plot, right? Let me plot. Let's say I'll fix some value c and then try to plot. Let's put value c is equal to 0 and just plot it. Okay, so when I try to plot, I would get like this. Let's say, let me call this is a y of x for c equal to 0. Okay, I hope my drawing looks okay. Now let me take c is equal to 1, right? C is equal to 1. The plot is slightly shifted. How? Because when x equal to 0, the y should be 1. So if this is a 1, so y value would be here. Okay, that means this x equal to 0 is this is y equal to 0 value is shifted of this old curve when I change the c value. So similarly, all the values are shifted by magnitude 1. So the next curve would be, you see, this is a curve. Let me call that curve as y equal to x for c is equal to 1. Okay, now you can just put c is equal to -1. Okay, so what I'm trying to do, when I'm trying to put c is equal to -1, the curve when x is equal to 0, what is the value of the y, which is -1. Okay, this is -1. That means the entire curve is shifted to lower when I put c values equal to -1. Okay, let me call this curve as y of x for c equal to -1. So what it implies is, for specific arbitrary constant c value, there exist, okay, there exist a family of curves. Okay, that means the same differential equation has so many solutions. So same differential equation possess so many solutions. What are those solutions? They are family of curves. Okay, very interesting. How this family of the curves are dictated or generated using these constants. Very interesting. Okay, so how these things are different is, like I said earlier example, x is equal to y equal to 3, 2x plus 3y is equal to 8. I'll get a fixed x and value. Use fixed x and y, but not family. But in the case of differential equations, okay, in the case of differential equations, unlike here, I'll get a family of curves. So it is not certain. So you have to keep on finding multiple solutions for the same differential equation as per the requirement. Another example, another simple example, like say, I'm not saying in the particular case, in many cases it's like that. So let me take another differential equation. Dy by dx is equal to another example. Okay, this time what I'll do, I'll say derivative is itself equal to the function as it is. Okay, again, let's try this. We just solved earlier by what? By doing rearrangement. Okay, integrating, which gives me log y is equal to x plus some c prime. Y, if I send a log to the right side, it will become exponential x c prime, which is, let me call some c exponential c prime as some c e of x. So my equation is, the solution of the system of differential equation is exponential function multiplied by some arbitrary constant. In this case, if you try to find what is the nature of the solutions, if you try to plot them, you see, okay, if you try to plot them here, see, when let's say c equal to 0, right? In the case of c is equal to 0, I'll get everything is horizontal. Okay, right? So nothing, no interesting stuff happens. Okay, when c is equal to, let's say, 1, when c is equal to 1, okay, if c is equal to 1, what happens? When x equal to 0, y value would start at 1. Okay, so then you just increase the x value, it would go to exponential increase. Okay, so this is function which is y of x. which is equal to exponential x, where c is equal to 1. Okay, now let me change c value. Let's say c value is 2. In that case, what happens? The same exponential function is slightly shifted, so it will go like this. Okay, so this is y of x is equal to 2 into, okay, refresh. Okay, where is the drawing? Okay, anyway, let me take. So y equal to c into exponential x would happen to be like this, like this, like this. Okay, when c is equal to 1, c is equal to 2, so y value would shift slightly. Again, there is a family of curves. Family of curves. So they are solutions of differential equation of this. Okay, so remember, always a differential equation would not have a specific solution. It may have multiple solutions. Okay, that is conveyed now. Okay, so now get into the nature of solutions. What kind of different solutions we may have. Okay, right? So let's get back to our old definition, where differential equation is what? A differential equation means it will have independent variable, it will have dependent variable, it will have the derivative of dependent variable with the independent variable. Not only just one derivative, it may have higher order derivatives also, and so on. Let me say it as nth order derivative. Okay, right? So the system is represented by, let's say, some function, a derivative function, which is equal to 0. Okay, so this is the definition of differential equation, right? So if you solve it, what you get is what is y of x would look like. Y of x would look like, in general, okay, add label, show checkpoints, add drawing. Okay, so f of x, by solving, you would get a what is the function. Now let's understand this. Okay, to find the nature of the solution. So we want to understand the nature of the solutions. Okay, nature of solutions of DE we want to understand. Okay, how do we understand? Let's take a simple example. Okay, let me take an example. Y double star, a double prime, is equal to y single prime plus y itself. It's a differential equation. Okay, so just now we saw a differential equation solutions look like an exponential function. Okay, what you can do, you can just make a guess. One could simplify and verify what could be differential solutions of this differential equation. One thing and one people can easily check is, let me take a differential equation with a solution exponential 2x. Let me call another solution, because any kind of solutions could exist, 3x. Okay, right? Does this solution satisfy this given differential equation? Okay, right? So that is what in complexity theory, right, we usually see whether differential these equations could be solved, or this given solutions we can check for the given equation, the given solutions are satisfying or not. Okay, let's try to check in that way. So given y1 exponential 2x, given y2 exponential 3x. Okay, so does it satisfy this given differential equation? Let me take a LHS. Okay, let's substitute exponential 2x, exponential 2x. I have to do double derivative minus 5 into single derivative plus exponential x as it is. Exponential x as it is. This is my left hand side. Okay, the single derivative gives just multiplication with the two exponential. Any exponential function derivative is itself with its exponent derivated accordingly. So if I do it once, I'll get 2. If I do it twice, I'll get 2 more. Exponential 2x minus 5 into 2 into exponential 2x plus 6 into exponential 2x. This is the LHS. Okay, let me take LHS common as a 2 of x common. What I get is 4 minus 10 plus 10. Okay, what is this happening? Okay, so this is messing up. 5 double star 5 my 5 plus 6. This is the equation we have. We're trying to check whether exponential 2x is solution or not. When I substitute, I'll get 2 into 2 exponential 2x minus 5 into exponential 2 into 2x plus 6 into exponential 2x. The LHS I am trying to understand. So which is equal to 4 minus 10 plus 6 into exponential 2x, which is what? 4 minus 10 is minus 6, minus 6 plus 6 is 0, so 0. So which is RHS. Yes, this is a solution. Okay, I did not solve, I just by guessing the differential equation has some exponential solutions we saw earlier, so I tried to substitute. Even you can just check this solution also. Okay, let me increase the thickness. Exponential 3x. Okay, let me check again. Take the differential equation and substitute. When you do twice derivative, you get 3 into 3 exponential 3x minus 5 into 3 into exponential 3x plus 6 into exponential 3x. The LHS, this is happening. LHS is equal to this. So I have 9 minus 15 plus 6 exponential 3x. Okay. So if you just see this is 0. So which is equal to 0. I got RHS. Okay. So even this is also solution. Right. So I have not solved any differential equation, but I just guessed what could be solutions of this differential equation. So by guessing, I got two solutions. One is exponential 2x, another is exponential 3x. What I can do is a second order differential equation. Remember, it's a second order differential equation involving two second order derivative. It must have at least two independent solutions. This is one independent solution. There is another independent solution is exponential x. So you can generate a generic solution from the independent solutions. How? You just add them together and you get a generic solution. A general solution for D, which is y double star minus 5y plus 6y is equal to 0. For this differential equation, I have a solution. Okay. Remember, I can keep going guessing multiple solutions. I can guess little more. But thing is, how long I can keep guessing, right? So since it's a second order differential equation is there is a must and you should have at least two independent solutions. Okay, that is must. Two independent solutions is must because the second order differential equation. If it is a third order, you should at least find three independent solutions. Then at that point, you can generate a general solution out of whatever independent solutions you got. Okay, right? So that is about second order differential equation for you, right? So now all the way, if I just given a differential equations, let's say y star is equal to 2y, right? If I have a differential equations like this, right, which is whose solution is dy by dx 2y. If you just rearrange, dy by y is equal to 2 into dx. If you integrate, okay, example, I'm trying to take one more example. So if you try to integrate, log of y is equal to 2 into x plus some c prime, right? Some c prime grab image, copy to Google. Okay, right? So dy by dx is equal to 2x. I'm trying to solve, and whose solutions are y of x is exponential 2x, okay, multiplied by some c, right? Okay, now the question is, how do I find c? It's very easy. Let's say the initial condition of the system is there. Initial condition, okay, is given. What is that is, let's say y x is equal to 0. If initial condition is given y1, then I can easily find what is my c. Okay, so the initial condition importance, what it does. So in this particular case, if I substitute y of 0, exponential 2 into 0 into c, which is actually 1, which implies c is equal to 1. So therefore, y of x is just simply exponential 2x. Now I got rid of the arbitrary constant. Okay. Sometimes even people give not the initial condition, they also give the boundary condition, like boundary condition. What is that is, let me say y x is equal to L, some later values, it is equal to, let's say it takes value 20. Okay, in that case, let me substitute y x equal to L, which is equal to exponential 2 into L, c is equal to 20. That implies c is what? 20 by exponential 2L. Okay, therefore, what is y of x? Y of x is exponential 2x multiplied by c, which is 20 by exponential 2L. In short form, you can write down 20 into exponential x minus L. So this is a solution. Even the boundary, extreme boundary values is used to find. Okay, right? So we know the different kinds of solutions so far. Now, unknowingly we are trying to do something here. What is that is, the solving technique unknowingly we are using, that unknowing technique is called a separable technique. Okay, what is that is, if a differential equation is given, let's say y prime is equal to, let's say 2xy is given, okay, and it is allowing me to separate like terms into one side, dy by y dx into dx. Okay, separability is allowed. That's why you are doing, and you are trying to integrate. So you will get a log of y is equal to 2x square plus c. 2 gets cancels. Y is, let me put, this is psi prime, y is c into exponential x square. You are doing, okay, right? So let's say if I have a differential equation is given like this. Okay, counter example. Let's say y prime is equal to x square plus y square. Okay, is it possible to separate? Let's see. Dy by dx is equal to x square plus y square. To take this equation, it becomes impossible to separate. Impossible separate. So the separable method which we are doing unknowingly is not possible in every scenario. So the conclusion is separability is not confirmed in all DE types. Only particular types where separability is there, those differential equations called differential equations which are separable. Okay, right? So we have to be very careful. Let's say the separability is not possible. What one can do in that case? We will see there are different kinds of differential equations which would be solved in a particular way. Okay, now depending on the order for differential equations, we are solving. We are so far we solved the second order differential equations and first order differential equations throughout our undergrads, grad, and so on. Okay, right? So let's specifically try to from the scratch. Let's say I have a differential equation of the first order. I don't have a second order derivative. Let's say I have a differential equation first order is there, right? Where I have y and also y prime. Okay, now I bring something more. I say if y prime is directly proportional to y, so then those differential equations I am calling as linear differential equations. What there is a y prime is directly proportional to y. What it means is y and y prime never come together in a differential equation. Okay, they never come together in a differential equation. What is the differential equations would look like? Let me see. Okay, so what is the differential equation would be the y prime and let's say let me call ax into y is equal to b of x. The constants, so far I have taken constants. Let me take the constants. There are also some function of some variable, independent variable. Okay, so these differential equations are called, linear differential equations because you see y and y prime are never coming together. What it means is y prime is directly proportional to y. Okay, now I can just rearrange this. Y prime is equal to bx minus ax into y. Okay, I can solve this, right? If you carefully see here, if I just rearrange, what I see is y prime is directly proportional. Okay, here what is the proportionality constant? Proportionality constant here is proportionality constant is ax with a negative sign, and there is a shifting constant. There is a shifting constant which is in this particular case Vx. Okay, so those are, if you see any differential equation where y prime y double prime are never multiplied to each other, then you can just simply say they are linear differential equations. Okay, right? So this is actually comes from the idea of linear equations, right? So what are the linear equations you see in algebra? If y and x, if you just to say, if I just take y straight line, y equal to x, it's a linear equation, it's a line. Okay, if I just take y equal to 2x, it's shifted. Okay, right, slightly shifted, it's much more quicker. Okay, y equal to x by 2, right? So there is a linearity. But if you just take an equation y equal to x square, it's called non-linear equation because the solution is parabola. Okay, right? So here any change in x would not increment y in the same way. Change in x, actually y gets doubled increment wise. So that's why I'm not getting a straight line, I'm getting a curves. Okay, non-linear. So the solutions of these differential equations would also be in the form of straight lines, right? So that's why they're also called a linear, and there is a relation is y prime is directly proportional to y. Okay, right? So if y prime is directly proportional to y square, then we might get a non-linear curves. That's the curves I'll get. Okay, so that is the non-linearity geometrically and also mathematically. The mathematical relation, this is a mathematical understanding. Okay, and geometrical understanding, right? We usually don't give much attention to these things. That is what I want to touch. Okay, now so let's take this kind of a differential equations and try to find the solutions. Okay, right? One example, let me take an example. Y prime. Okay, so y prime plus 2 into x into y is equal to x. Let me take one interesting equation. Okay, so what I see here is y and y prime never comes together, they're proportional to each other. Okay, now if this kind of a solution equations are there, for sure I cannot separate them. The separability is not possible. Okay, I have to look for some other technique to find. So what is the technique is, let's recall back earlier the equation which I wrote, which is y prime plus a into x y is equal to vx. Okay, if this equation I have given, okay, so here I can solve this equation, right, by using something called by multiplying the entire equation by something called integrating multiplying the integrating function. What is the integrating function is, you take whatever is multiplying to the function, you take that a of x and integrate that a of x, okay, and put that whatever solution in the exponential. So this is a factor, integrating factor. If you take this factor, okay, multiply onto this entire equation, doesn't matter, no? For the entire equation you are going to multiply. If you try to put this entire thing, multiply this entire equation, what happens then? If you do that, it leads to me a path to solve differential equation with ease. Okay, maybe it will allow me to find the separability, or it would allow me to find how to solve it. Okay, let's try to check that. So just to compare this equation with this equation, what is there in the place of ax? Ax is 2x. Then if I have to integrate ax with the dx, which is equal to 2x dx, 2x, oh my god. This is close, take, close, and drawing. Okay, so what I'm trying to find, I'm trying to find integrating function. So which is exponential 2x dx equal to exponential x square by 2 plus c. Okay, for the time being, let's ignore this c part. Ignore. Okay, why am I ignoring is, okay, I'm just trying to find integrating function. Okay, integrating factor. Okay, so that factor which I am going to find, I multiplied throughout the entire equation. So ignoring c, it's not going to make any difference because it is there throughout, it gets cancels on the both sides, so I'll not want to bother. So let me call the integrating function, let's say mu is exponential x square by 2. Okay, so differential equation what I have is y prime plus 2xy is equal to x. This is I have, it is non-separable. Okay, non-separable. So what I'll do, I just multiply the entire equation by this factor. Okay, remember, how do you find mu s? From the equation itself. Okay, so let me substitute multiplication x square by 2 into y prime plus 2xy ex square is equal to x into ex square by 2. Okay, right? So you see here on the left hand side, what I see is two terms. Okay, so interestingly, by looking at these two terms, I can just guess something, that is, if I just take a function, y exponential x square by 2, if I derivate that function with x, okay, what I get? First, let me derivate y, and the algebra exponential function, I leave it as a second term, y prime x square by 2. If I differentiate the second term, I'll get 2x exponential x square by 2. You see, this is this. That means I can write the left hand side as derivative of y into x square by 2. On the right hand side, I have x into x square by 2. Okay, right? Now send this derivative of dx to the right. So what I get is change in y multiplied by x square by 2 is equal to x ex square into dx. Right? Even though I am not able to separate, but I am able to put things in such a way I can easily integrate. Left hand side, some change, overall change. On the right hand side, integration of integrand with respect to x. So left hand side, when I integrate, I'll get y into x square by 2. Okay, so derivative and integrate gets cancels, right? So I'll get a left hand side y into e to the power of x square. But right side, I want to do, there are two functions. One is algebraic function, exponential function. Let me substitute x square equal to t. 2x derivative 2x dx is equal to dt. X dx is dt by 2. If you substitute, let's say I don't know the limits. Okay, if you substitute, what I get is x dx becomes dt by 2. Okay, exponential x square by 2 becomes et. Now you can integrate easily, which is 1 over 2 et plus some constant. Now let me put some constant literally. Okay, now send this to the right. Y is equal to, okay, 1 over 2 ex square by 2. Let me put back my t as it is, divided by exponential x square by 2 plus c x square by 2. Okay, this cancels. What I am left with is function y of x is 1 over 2 plus c by, or c into minus x square by 2. I got a solution. You see, this equation which I had earlier, it is not solvable, it's not separable. Okay, and what did I do? I found the integrating factor. It's called integrating factor. which is generated from where? It's generated from the information from the equation itself. From that equation, we found that factor and we able to reduce the differential equation into much simpler form so that I can integrate with ease and find the solution. You see, it is much easy, right? Okay, so this is one technique. One technique unknowingly we are doing separable method. Another technique is using the integrating factor. Okay, very important. So another technique which is being used in the throughout the studies is something called reduction method. Reduction method. Guys, if you have any doubts, please do ask now. I will give a break for a few minutes if you want. Reduction method. Let me see if there is any questions. There are questions. By solving the differential equations, do we always get exponential set of values? Very good question. Okay. No, not every time, right? We will see different kind of solutions. Only particular linear differential equations, probably yes, right? In some cases, but not all, right? So the best way to do is let's take some exponential function, substitute into the given differential equation and see whether that satisfies or not. If it satisfies, well and good, you hit the jackpot. Otherwise, you have to literally find the solutions. Okay, right? How to guess? Yeah, how to guess? So let's say there is a proportionality. Let's say I was giving directly proportionality, linear. Okay, so in that case, exponential functions, right, or sine function, cosine function, right? So, but the thing is, there are multiple methods. Variable separable method, that is we saw, and integrating function is another technique. There is multiple techniques are there. We have to explore those techniques and try to find solutions. Okay, we'll see. Actually, you just get to see that. Okay. Is it y or x on the right, RHS? Okay, probably you're talking about I think this equation. I think this equation is x on the RHS. Okay, you can go back and see in my notes. It is there specifically. I have not made any mistakes with writing y or x interchangeably. Okay, will you giving a break in some time? Yeah, I'm just giving a break now. Right? So it 2 cancels out with multiple of 2. No, if there is any cancellation, it will not. Okay. Right. Reduction method. Before going to the reduction method, please take a maybe few minutes break, maybe 5 minutes break. Let's say we'll assemble back at 3:20. Okay. And 3:20 we will get back to another technique.
Thank you, sir. We are also trying to schedule these lectures in such a way that we'll have a break